Now, how do we look at the energy diagram? How do we even draw an energy diagram for if you have a two-step reaction mechanism? So we talked about one, now we're talking about two. So you can have three, of course, and four, etc., but generally we examine a two-step mechanism. Each step of a multi-step reaction has its own characteristic rate. So you cannot just assume that one is going to have a high, just because the first step has a high activation energy, that the second one is going to have the same. So that is not true. So again, each step has its own characteristic rate and therefore its own transition state. The reaction can occur no faster than the slowest step. In a multi-step reaction, the slow step is called the rate limiting step. This is very important. You cannot move faster than the slowest person in your group. You have to take a trip to somewhere and you have to take someone else with you and they're driving in their own car. You want to reach that destination together. Otherwise, the other person doesn't know the directions. You would have to go by the speed of that person. It's as simple as that. So you cannot have a faster rate than your slowest step, which is the rate limiting step. Very well. Only the concentration of reactants affecting the rate limiting step appear in the rate equation. So you cannot put both, if you started with both, only the ones that are affecting the rate limiting step. You cannot put both if one does not apply. So let's look at this equation. Since the rate depends on the concentration of C, which is right here, only CD is going to appear. So if you look at this reaction, it's unlike the one we talked about. This is a two-step reaction. This is the only one. This is the only one that you actually are concerned about. So what do I mean by this? We may need a little bit more space here. This is what I mean. If you double CD, you double the reaction rate. If you double E, okay, then there's no change in reaction rate. And the reason why is because the reaction rate would be R equals K times the concentration of CD. Notice that E is not part of it. How do you know that? At this point, of course, you don't know that, but I'm just telling you that in the reaction rate, only the concentration of the reactants that has an influence on the reaction rate is written in the equation. So you cannot write E in here unless it has an effect. And in this case, it has no effect. There's no change. This one doubles. Since it was found that the reaction rate depended only on the concentration of CD, therefore, the mechanism is consistent with the rate law two-step process. So actually, this is two steps right here. So the two steps are the following. This is step one. And what happens is that this is a heterolytic bond cleavage. Notice that the electrons went with C. And of course, they created a reactive intermediate. Right here, D is a reactive intermediate. And then this is your nucleophile attacked D, so that would be your step two, created DE as the product. So notice how it's two steps. This did not go from CD to DE in one step. It had to break the bond first, create C as an anion, D as a cation. This is your electrophile, and then this is your nucleophile, and then this is your final step. So this is called a first order reaction because, again, it depended on the concentration of CD right here. Okay, so again, first order means, or unimolecular means only one reactant that is controlling the reaction rate. Second order means two reactants, like we did see in the last one. So here's your step one, there's your step two. How do we apply this here? Like I said, it's not really bad. You just have to take a look and understand where things go. So before we do that, we have to take this now, our reaction mechanism, and apply it to the reaction diagram, the energy diagram. So obviously this is your C, D, and E. You start here. So these are your reactants. So C, D plus E minus. That's what you're starting here. Then you go to the transition state. This is called the first transition state. So this would be TS1. And let's take a look and see what is happening in the transition state. So C is breaking. C is breaking away from D. So it would look like this. C with a dotted line to D like that. Okay. Now, once again, the delta minus goes on the atom that's taking the electrons with it. So C is taking the electrons, D is keeping no electrons. So that's how you would show it. Okay, where's the EA, the activation energy for this first step? Correct, it's right here. Let's actually use a different color. Okay, I'm drawing this because remember, we need the difference between the reactants and products. So this would be right here. This would be the activation energy for step one. So we would call this EA1. Very well. So where's your step one? It's going to end here. So this would be from this to that, that would be your step one. From here, I'll show you. Let's draw the second one and then I'll show you what step one is on here. So then the next step would be that C now would be attracted to D. C is reacting with D. But what you have here is you have your intermediates. So what happens is that at the peaks, you have your transition state. In those wells or the valleys, you have your intermediates. Just keep that in mind. So we have C minus, and we have D plus, and of course, E minus. These are our intermediates right there. Okay, transition state. The formation is between D and E, so that would be D dotted line to E. Which one has the electrons on it? That would be E, so that's a delta minus. And that would be a delta plus. Okay, do we have another transition state? There it is. Do we have another EA? Yep, here it is. It's hard to draw, but it's in between right there. So that would be EA2. And that would be, of course, right here at the top would be our TS2, second transition state. And then finally, the products are formed, and you have DE plus C minus. So these are our products. Very well. So what's the difference in energy between products and reactants? That would be our delta H. And of course, it is negative, meaning it's an exothermic reaction, which is favorable. Where is step 1? So I'm going to use, I know it's going to become fuzzy, but let me show you. Step 1 is basically this. This is step 1. So step 2 would be this right there. Which one would be my rate limiting step? It's the one with the higher activation energy. The step, or it's actually answered down there. I'm going to say it's a step 2. Step 1, my apologies. It's the one with the highest activation energy right here. So the rate limiting step is the step with the transition state of highest energy right here. And of course, the rate of the overall reaction cannot be higher than the rate of the rate limiting step, as we said. So your rate again would be R K equals C, the concentration of CD. So that's how you should think about it. So again, take your time to actually practice and absorb this. I just put another one here on catalysts. What catalysts do is they lower this activation energy. And that's how enzymes actually do that. We will probably do some in the discussion on examples of how enzymes lower the, they do catalysis in terms of the organic chemistry.